Welcome to our video today. Today's video is going to be on the topic of perpendicular bisector converse theorem. And we're on page 339, continuing activity 1, which is all about the perpendicular bisector theorem. If you haven't yet, make this note card, right? This is the back of it. If a point is equidistant from the endpoints of a line segment, then the point lies on the perpendicular bisector of the segment. It's on page 339. This is the picture that you should be seeing as you are creating it. Let's get into it. For this video, you're going to need a highlighter. You're probably going to need something to write with as you make some notes. And then I went ahead and I actually wrote down like a whole paragraph, like, like a Mad Lib sort of thing you're going to need to know. So go ahead and pause the video at some point just so you can get this stuff ready, and we're going to fill in the blanks together. Okay? Pause right here. Write it down. That's a good pause. All right, let's get back. Here we go. Welcome. Okay, so let's go through the worked example together first. So highlight, process, annotate whatever information we have that's in this space. Analyze the proof of the perpendicular bisector converse theorem. That's our focus. That's why I've got that note card. It says, given points Q and R are equidistant from point P. That's a vocabulary word that you need to know. In fact, I'm going to go ahead and zoom in so it's just the processing of this section. Equidistant, reminder, equidistant means the same distance away. And equidistance is visible by those yellow spikes. That's where the equidistant is coming up. You can draw an auxiliary line from Q to R. So it's a line segment. Draw an auxiliary line, and this is the auxiliary line that they're drawing. In fact, I'm going to put a little label like that's what they mean by the aux line. Right? You have this auxiliary line. It forms an isosceles triangle, right? We know we have an isosceles triangle. So another vocabulary word. In an isosceles triangle, in the three sides, two of them are the same length. So our triangle here is isosceles. Two sides are the same. Now, construct the midpoint of QR. And our method for constructing midpoints is actually to do perpendicular bisectors. Because when you perpendicular bisect a line segment, you find the midpoint. The perpendicular bisector will be on the midpoint. Or you could just straight up measure it. You could be like, this is approximately 3.2 centimeters. And so 1.6 centimeters would be the middle. You could totally do that too. In fact, because I did measure it, I'm going to pop that in here. This is 1.6 centimeters. This is 1.6 centimeters. That's how I know that I've got the midpoint M right there. You can draw another auxiliary line. So there's that word auxiliary again. In this case, the auxiliary line is right there. It's the line between P and M, right? The midpoint and P, when you connect them with a line, that's just another line that you drew called the auxiliary line. The two triangles, so there's triangle PQM. Again, have some highlight here. PQM is the top triangle. And where we're at here, I'm going to use a different, I'll use pink for this one. Triangle PRM, so PRM. Those two triangles are congruent by something we like to call side, side, side. Now, I know that it's side, side, side because this one spike PQ and this one spike PR are equal. I know that QM and RM are equal because I measured. They're both 1.6 centimeters. So QM and RM are equal. And then last of all, PM in the yellow triangle is the same PM for the pink triangle. So PM equals PM. These are all sides, and that's what we mean by side, side, side. That is also allowing us to then, therefore, prove and say that the angles inside the triangle are congruent by CP/CTC. Corresponding parts, like angles and sides, of congruent triangles are congruent. So if we've got two congruent triangles and we've made a list of the sides that match, we can also make a list of a couple of angles that match. So those angles would be PMQ, that's this angle right here. And then we've got PMR, so that's this angle right here. They're both congruent because they are matching angles in both of those triangles. Since these two angles are congruent and form a linear pair, oh my word, I gotta make sure I talk about our vocabulary word of the day. Linear pair. A linear pair when you have two angles and they meet to make a line. Just like in our picture of our notes, right? In this picture, the angles right here are along the line QR. So therefore, they're a linear pair, but they're both equal. And the only way they can both be equal and form a linear pair is if they're both 90 degrees. That means PM is a perpendicular bisector. It's exactly in the middle of QR, and the line that it creates with P, M to P, makes both of these 90-degree angles. And so I'm going to pop a little 90-degree box on there. That's our proof. P lies on the perpendicular bisector of QR. Okay, so there it is. We've talked about P is the same distance away from 2 points on a line segment. And if you draw the line that meets, like goes from P through the middle of that other line segment, you've drawn a perpendicular bisector. We get to say that that's the converse, right? The converse, because you started with knowing equidistant, you didn't start with perpendicular. It's after you know that the point P is equidistant, do you then get to say it's on the perpendicular bisector. See the order? It kind of like flips from like the way you thought about it or the way we've been talking about it in class or thinking logically. It's the other way around. It's still true. We have a proof of it. Let's finish question 3 and finish this video out. Let's go. Okay, so a little minimization of the window where I am, and maybe move it over there. All right. Consider the worked example. How would you know that point P lies on the perpendicular bisector of QR? Well, if point, fill in the blank, if point P is equidistant from points Q and R, using the picture from up above, well, then point P lies on the perpendicular bisector of QR with a little segment line on top of it. That is our statement. That is our reason from the proof. So we have point P is equidistant. It must lie on the perpendicular bisector. And so that tells us our perpendicular bisector theorem on page 339 is ready for us to comment on in this video. If a point is equidistant from the endpoints of a line segment, then the point lies on the perpendicular bisector of the line segment. Bam! What?